Good morning. Today let us discuss microprocessor 6. So far we have seen microcomputer, 8085 based microcomputer, and how to write programs for it, how to interface memory and I/O devices. And now in today's class let us see direct memory access, serial I/O communication, and some applications. So today's objectives are conditions of data transfer we see, then DMA and its advantages, serial I/O data transfer, communication interfaces importance, and lastly list typical applications of microprocessor. Let us start our discussion with conditions of data transfer. Look at this chart. This describes various conditions of data transfer between microprocessor and peripheral. First, based on transmission format, microprocessor communicates with peripherals in two ways, asynchronous and synchronous. In synchronous, meaning of synchronous is at a time. In this method, data transfer between processor and peripheral will be done at a time. For speed data transfer, this method is used. And next method is asynchronous method. In asynchronous method, it means at irregular intervals of time. Processor communicates with the peripherals at random times. That is, peripheral do not know when the transmitter is going to send data to it. In this method, processor has to tell the peripheral when it is starting and when it is stopping the actual data. Hence, it must start with a specialized character bit, in this case called start bit, and it must end with stop bits. One byte or one character will be transmitted at a time in this case. Hence, the speed, that is data transfer speed in asynchronous method, will be relatively less in comparison with the speed of synchronous data transmission. And next, based on modes of data transfer, parallel data and serial data. 8085 microprocessor is basically a parallel device, that is, it transfers 8 bits of data at a time. So far whatever we have discussed, all of them comes under this parallel data transmission, because 8 bits were transferred from the processor to the peripheral or memory location at a time. And next method is serial data transmission. In serial data transmission, one bit will be transferred at a time. Either it will be sent or received by the processor to the peripheral. There are some devices like cathode ray tube, magnetic tape. They solely work with serial data, and because of the advantages of in using serial data transmission method has become an important part that we will discuss. And next, based on types of I/O, already we have discussed. Processor identifies I/O devices in peripheral I/O, that is called I/O mapped I/O or peripheral I/O, and memory mapped I/O. In last session we saw this. In peripheral I/O, processor identifies peripherals as peripherals or I/O devices only. It uses in instruction and out instruction for data transfer. And in memory mapped I/O, microprocessor identifies I/O devices as memory locations. Hence, it uses 16-bit address for identifying I/O devices, and all memory related instructions like move M2R or move R2M or store accumulator and so on, all memory related instructions can be used for data transfer. And next category is actual conditions of data transfer. In microcomputer system, data transfer happens in two ways. One is under microprocessor control. Larger part of data transfer happens in this mode only, that is under the control of microprocessor. And there is also another method called device controlled. If the peripheral or if the device can transfer data with faster rate than the microprocessor, then microprocessor can relinquish its buses and hand over it to that particular device which can transfer data with faster rate. So, this method is called DMA, direct memory access. Microprocessor uses hold signal for doing this. Now, let us see in detail microprocessor controlled data transfer. These can be divided into basically 5 groups. First one is this unconditional data transfer. In this situation, processor assumes that the device is always available. Hence, processor sends data to the device as and when it wants, and after sending data, processor will go on executing its next instruction. Example for this is LED ports, and whenever data is sent to LED port, simply LEDs will display it. This is unconditional data transfer. Next method is polling. In this method, first processor checks whether valid data is available or any data is available at the device. Then, in other words, if the device is ready, then only microprocessor will start data transfer. Example for this is keyboard. Processor will be looking at the keyboard, that is, it will execute keyboard related instructions in a loop until some key is pressed. When some key is pressed, then only processor will read that data. So, this type of communication with the device is called polling method. And next method is interrupt method. The drawback of the polling method is processor wastes its time in just observing the device whether it is ready or not to check it. That is overcome by this interrupt method. If the device is ready, it simply interrupts the processor, then processor will take care of transferring data. So, processor precious time is not wasted. And next method is with ready signal. You know, microprocessor has a pin called ready. It is used by normally low speed peripherals. Since many peripherals speed is less in comparison with the execution speed of microprocessor, peripheral may require more time. Then it simply activates ready pin. Then microprocessor introduces extra T states. As a result, the execution time will be increased. So, during that extra time, device can safely transfer data. So, that is the importance of data transfer with ready signal. And last group is with handshake signals. In this particular group, prior to the data transfer, microprocessor and device exchanges some signals. Those signals are called handshaking signals. These handshaking signals ensures proper data transfer without error and also help in synchronizing the data transfer. This is of two methods, again status check and interrupt. Status check is equivalent to polling. In this, processor will be looking whether the device is ready or not. If the device is ready, then only data transfer will take place. And in interrupt method, when the device is ready, that interrupts the processor so that processor can handle data transfer. So these are the various conditions of data transfer. In this particular class, we will be seeing device controlled, that is direct memory access, and we see some of the things in serial data transmission. Next, let us see DMA or direct memory access. The direct memory access, DMA, is a process of communication or data transfer controlled by an external peripheral. That is, if the external peripheral like DMA controller can transfer data with faster rate than the microprocessor, then that external device controls all buses, that is address, data and control buses, and takes care of transferring data. For doing this, you see, in situations in which the microprocessor controlled data transfer is too slow, the DMA is generally used. Example, data transfer between a floppy disk and read-write memory of the system. For doing this job, microprocessor has two pins, hold pin and hold acknowledge. Let us see it in the next slide. The 8085 microprocessor has hold and hold acknowledge pins available for this type of I/O communication. First, let us see hold pin. Hold is an active high input signal to the 8085 microprocessor from another master requesting the use of address and data buses. Here you see request is from another master. In this case, DMA controller is equivalent to that of microprocessor. It can work with the speed of processor, and because it can do limited operation, in this case just transferring data, whenever it can transfer data, it asks the processor for the buses with the help of hold signal. Now, hold, after receiving the hold request, microprocessor relinquishes the buses in the following machine cycle. All buses are tri-stated and a hold acknowledge signal is sent out. This hold acknowledge signal informs the DMA controller that microprocessor has relinquished the buses. Next, the microprocessor regains the control of buses after hold goes low. So until data transfer takes place by the DMA controller, this hold pin will remain high. After completing data transfer, this hold pin will be made low by the DMA controller so that microprocessor regains the control over the buses. Next pin, hold acknowledge pin. Hold acknowledge, this is an active high output signal indicating that the microprocessor is relinquishing the control of the buses. That is, these will be all the buses will be in tri-state, that is in high impedance state, so that these buses can be used by DMA controller. Now, let us see this block diagram. This is a simple microcomputer system which has microprocessor, memory, I/O devices. This is like a floppy disk drive which can act as input device as well as output device, and this is DMA controller. 8257 is a popular DMA controller. Initially, this DMA controller is also just like any other peripheral. That is, it will be in what is called slave mode. In this mode, 8085 microprocessor identifies DMA controller just like other peripherals and writes control words initially into it. This DMA controller has 4 channels, that is I/O devices are connected to this DMA controller. 4 I/O devices can be connected, and each channel has two 16-bit registers. First register, 16-bit register, is used for holding the address of memory location from where it has to transfer data, and next 16-bit register is used for holding the count, that is how many bytes has to be transferred. First 2 bits of the second 16-bit register are used for direction indication, and 14 bits are used for actual count. Hence 2 power 14, that is 16 kilobytes of data transfer is possible from each and every channel. And 4 I/O devices can request this DMA controller. Inside it there will be a priority resolver which determines what I/O device to be served. After choosing that particular I/O device, this DMA controller will send an acknowledged signal to that particular I/O device, so that data transfer with that particular I/O device takes place. Let us see how data transfer occurs here. First, I/O device in this particular case is connected to channel 1 through DMA request pin. See, I/O device is requesting DMA controller. As a result, DMA controller activates its HRQ pin, that is hold request. Because 8257 is now under slave mode, it requests microprocessor to relinquish the buses so that it wants to make use of it. After receiving this hold signal, 8085 microprocessor completes its current machine cycle and activates hold acknowledged signal, that is it sends hold acknowledged signal to the DMA controller, indicating that it has relinquished the buses. Now when hold acknowledged is received, DMA controller sends DMA acknowledged signal to the I/O device. So this DMA acknowledged signal is normally used to select that particular I/O device. After selecting it, DMA controller now sends address and identifies a particular memory location. Then DMA controller sends I/O read bar signal to the I/O device, in this case floppy disk drive. In response to that, I/O device places data on the data bus, and simultaneously DMA controller sends memory write bar signal to the memory. As a result, memory will take data from the data bus and store it in the specified memory location. This way 1 byte is transferred from floppy disk to the memory, and this will be continued until all bytes are transferred. When 1 byte is transferred, the count register gets decremented by 1 until this will continue until count register becomes 0. So in this case floppy disk is sending data to memory, hence it is a memory write. Next, let us see if memory wants to send data to floppy disk. In this case, when this floppy disk is ready, it requests DMA. Now request is made through channel 2, you observe it through DRQ2 pin. In response to that, 8257 activates hold request signal. It is very similar to the previous case. When hold signal is received by 8085 microprocessor, then it completes current machine cycle, and then it activates hold acknowledge signal. When this hold acknowledge signal is received by DMA, in response to that it sends DMA acknowledge signal to the I/O device which has requested. After receiving this, DMA places address of memory so that that particular memory location is identified, and it sends a control signal called memory read bar. In response to that, memory places data on the data bus, and at the same time DMA sends IO write bar control signal to the IO device, so that the data from the data bus is copied onto the floppy disk. This way data transfer happens between memory and IO device, in this case from memory to IO device. Again count will be decremented by 1 by the DMA controller, and next byte will be transferred in the same manner, and this will continue until all bytes are transferred. Now see advantage of DMA. Because of DMA, high speed data transfer is possible. In comparison with other methods, in status check IO and interrupt IO, data transfer is relatively slow because each instruction needs to be fetched and executed by the processor. Whereas in DMA, the DMA controller manages data transfer between memory and IO under its control, thus bypassing the microprocessor. So this is the major advantage of DMA. And hold pin of 8085 microprocessor not only used with DMA, it is normally used with other coprocessors too under multiprocessor systems. Now let us see serial IO data communication. In serial IO data communication, 1 bit at a time is transferred over a single line. For this, 8085 microprocessor uses SOD. This is one of the pin. It is for serial output data pin, and it also uses SIM instruction from its instruction set for serial data transmission. This is for sending data out, and for receiving data it uses SID pin, serial input data pin, and it also uses RIM instruction for data reception. And next, see, in serial transmission from microprocessor to peripheral, an 8-bit parallel word is converted into a stream of 8 serial bits. This is called parallel to serial conversion. Then 1 bit at a time is transmitted over a single line at a given rate. This rate of data transfer is called baud. Baud stands for bits per second. Technically it is signal changes per second. In serial reception, the microprocessor receives a stream of 8 bits and they are converted into an 8-bit parallel word. This is called serial to parallel conversion. In addition to the conversion, information such as the beginning and the end of transmission and error check is necessary in serial transmission. Before transmission, especially in asynchronous mode, microprocessor has to tell the peripheral when it is going to start. That is indicated by normally a start bit, followed by the actual data and error check. For error checking, during the transmission data may be corrupted. Whether the data is corrupted or not, that can be analyzed by using the error bit, normally a parity bit, or sometimes checksum is used or CRC code is used. In this particular case, let us assume we are using a parity bit, if necessary, that too, and followed by it stop bits. See this slide. An 8-bit message needs to be framed so that the receiver can detect correctly its beginning and end. Standard framing: start bit always 0 and stop bit always 1. Optional parity bit, that is we can use parity bit or not. Then stop bit can be 1 or 2 bits, and in this diagram you see start bit is low, that is it is going from 1 to 0, that stands for start bit. Then D0 bit of the byte, then D1 bit of the byte, and so on till D7 bit of the byte. 8 bits are transferred. Then parity bit, this is optional again, and stop bit is high, and we can add another stop bit for using 2 stop bits. Okay. Next Let us see this flow chart which explains how data transfer happens by using serial I/O method. Here during transmission, first set up character bit counter, that is how many bits we have to transfer, that count is stored in this register. Then send start bit, that is 0 bit, then wait bit time. After waiting for bit time, get character in accumulator, this is the actual character to be transmitted, that is brought into accumulator. Then output bit using D0, D0 bit of the accumulator is transferred. Normally for this, first D0 bit is transferred to carry flag, and then that is transferred to D7 bit of accumulator in the next instruction, so that by using SIM instruction we can transfer it through SOD line. And after transferring D0 bit, wait again for bit time, then rotate next bit in D0, so that next bit goes into carry flag, and that will be copied again into D7 bit, and then that D7 bit of the accumulator will be transferred through SOD line. After doing this, is it last bit? Like this, we transfer all valid bits, and here we check the count because we are decrementing the counter. If the counter it won't become 0, that means some bits are still remaining. So we repeat these instructions, that is taking D0 bit and outputting it. And if all bits are transferred, then add parity if necessary, then send 2 stop bits, then return to the main program from where it is called. This is how serial I/O transmission takes place. For serial I/O, for sending data through SOD pin, SIM instruction is used. SIM instruction makes uses of the accumulator contents. Interpretation of accumulator contents by SIM instruction. See, accumulator 8 bits are interpreted this way. The least significant 4 bits are used for interrupts, and D5 bit is not used. And with serial I/O, important bits are D6 and D7. D6 bit is called serial data enable. If this bit is 1, it enables SOD line. If this particular bit is 0, it disables SOD line. So for serial I/O transmission through SOD line, this D6 bit of accumulator must be made 1 before execution of SIM instruction. And next D7 bit, this D7 bit actually contains the bit to be transferred, SOD, that is serial output data. Whatever the bit available here, that will be put on SOD line. Let us see this program. Here in register C, the count 0B, here B for 11 decimal, that will be stored, and then exclusive RA accumulator, this is for clearing the carry flag, that is carry flag will be resetted to be used in the next instructions. Then move immediate A 80, here D7 bit of accumulator is made 1 and rotate accumulator right, that is 1. When this instruction is executed, all accumulator contents will be shifted by 1 bit to right, including carry. So since D7 bit is 1 and after execution of rotate accumulator right, that will be shifted into D6 bit. We have seen in the previous slide, D6 bit must be made 1 so that SOD line will be enabled. After that, SIM instruction is executed. You see in the previous instruction, D7 bit of accumulator will be is shifted into D6 bit. At the same time, carry flag, which was resetted by exclusive RA instruction in the previous instruction, that is also shifted into D7 bit. So this 0 bit of D7 is used as start bit. Then when we execute SIM instruction, 0 will be placed on SOD line, and we wait for bit time by calling this delay, call bit time. After that, we set carry by using this instruction stc, set carry flag. Then we take actual character to be transmitted into accumulator by using this instruction move B to A. In this case we are assuming the character to be transmitted is available in register B, and after taking it RAR, that is rotate accumulator right with carry, is executed, so that D0 bit of the accumulator is moved into carry flag, and carry which was set already, that will move into D7 bit. Now latest contents of accumulator are again copied into register B, so that it can be used in the next cycle, next loop. And since 1 bit is transmitted, now we decrement the counter. If the counter is not 0, then we go back and we execute all these instructions, so that next bit will be transferred. Like this we transfer all 8 bits including 2 stop bits, so that count becomes 11, and after that this will be returned, this subroutine will be returned to the main program. Next let us see serial IO receive. For the serial IO receiving, processor receives data through serial input data pin, and for this it makes use of RIM instruction, and after execution of RIM instruction, whatever the bit available at SID pin, that will be copied into D7 bit of the accumulator. Now let us see interpretation of accumulator contents by RIM instruction, that is read interrupt mask instruction. The least significant 7 bits, that is from D0 to D6, are used for interrupt. They show interrupt status. Only D7 bit is used with serial IO communication. In this case, after execution of RIM, the status of SID pin, that will be copied into D7 bit of the accumulator, and after reading 1 bit like this, it will be normally stored in another register, and next bit will be read after waiting for the bit time. Let us see those things in the flow chart. This is serial IO receive flow chart. In this, first read output port, and then it is checking is it start bit, that is if the bit is 0 or not, because start bit must be 0. If the bit is not 0, go back and again read the output port. So processor will be in this loop until output port becomes 0. Once it becomes 0, it waits for, it goes out of this loop and it waits for half bit time. After that it again checks. Here it is checking is bit still low, because due to some noise or some other reason, sometimes the input data may become 0 and it may not be valid start bit. To confirm that, it waits for half bit duration and it will again continue. If the bit is still 0, then it treats as start bit and then it starts receiving actual byte. First set up bit counter, it sets how many bits to be received, then clear register to save bits. In what register the received bits must be saved, that particular register will be cleared, and then wait bit time, then read input port, save that bit and get ready to receive next bit. So reading input port is done by using RIM instruction, and that particular bit is saved by using rotate accumulator left instruction, and then it checks is it last bit. If it is not last bit, it will go back and it will repeat. If it is the last bit received, then check parity if necessary and wait for 2 stop bits, then return to the main program. Now the same flowchart is shown left side and program to the right side. Here you see first RIM instruction is used and RAL instruction is used, so that the D7 bit is moved into carry flag. If D7 bit is 0, that indicates start bit. So in the next instruction we are checking that by jump on carry instruction. If the carry flag is set, it means it is not a start bit, so it will go back and it will be in this loop. If carry flag is not set, if it is resetted, then it waits for half bit duration and it sets count and waits for bit time, and next after waiting for bit time, it executes RIM instruction again, and then rotate accumulator left with carry. This makes D7 bit into moved into carry flag, and then decrement C, jump on 0, return. If the count becomes 0, that is if all bits are received, then it will go to next instruction. Here after receiving all bits, the bit here after when 0 flag is set, when that is when if all bits are received, then it will go to return last instruction. Otherwise it will go to next instruction. Here it places the bits saved so far into the accumulator, and by using RAR it shifts the bits to the right side, place the bit saved in carry into position D7 and shift all other bits by one position. Like this it will store all 8 bits. After storing 8 bits, it moves accumulator contents into B so that it saves the received bit sequence into register B. Here you see serial to parallel conversion is also happening and unconditionally it goes to receive next bit until all bits are received. Next this is so far whatever we saw, this is an software approach for implementing serial I/O communication, and this can be implemented by using hardware. For that we use 8251 programmable communication interface. 8251A is a programmable chip designed for synchronous and asynchronous serial data communication. It has 28 pins. So this is the pin diagram for 8251A. Quickly, D7 to D0 are data bus, C by D bar is control or data to be written or read bar and write bar, these are control signals, CS bar is chips enable pin, clock, CLK, reset, and TXC is transmitter clock, TXD is transmitter data. Next receiver clock, RXC, RXD is receiver data, RDY is receiver ready, TX RDY is transmitter ready, and next DSR, these pins are used with modem. DSR for data set ready, DTR for data terminal ready, this is sync detect and break detect. RTS is for request to send data, CTS for clear to send data, TXE for transmitter empty, VCC and ground So these are the 28 pins of 8251. This is the functional block diagram. Data bus is connected to data bus buffer and all control signals are connected to this control logic, and DSR, DTR, CTS, RTS, these are used with modem. And the important part is transmitter and receiver. This transmitter buffer, it first converts parallel data byte and into serial data, and then it sends through this TXD pin. If byte is transferred, that is indicated by transmitter ready pin, this can be used to interrupt the processor to send the next byte. And the transmitter in empty, this indicates output buffer of the transmitter is 0, that is all bits are transferred. This is the transmitter clock. And with the receiver part, you see receive data, after receiving bits this first converts serial to parallel conversion so that byte can be used by the processor. Okay, and this receive ready is used to interrupt the processor, this is the receiver clock, and sync detect, this is used with synchronous communication. Normally 8251 is used in asynchronous mode by the processor. Now we see advantages of microprocessor control over discrete logic control. First one, replacement of discrete logic based circuits. The problem with discrete logic based circuits is it is not easy to introduce changes into it. For that we have to change entire circuit many times, whereas if we use software approach with the help of microprocessor, then simply if we change the program, that will do the job. So next one is provide functional upgrades. It is whenever there is an improvement, that can be simply copied into the processor's memory and we can make use of it. Provide easy maintenance upgrades, and similarly improve mechanical performance. Here if for example if you take some connector, all the pins of it can be redefined by using software instructions, hence it improves mechanical performance. We need not change the design of the connectors. Next, protection of intellectual property and replacement of analog circuits. Here the analog circuits, the advantage of replacing them with digital circuits, first it saves lot of power, and all digital technology advantages can be retrieved from this. Next, microprocessor applications. Here we are seeing few applications: traffic controller, temperature controller, scanned LED displays, and importantly processor is used as CPU in computers. And there are many other applications like lift control, that is called elevator, and so on. Now we see one application, that is traffic controller. So this is the diagram. In this particular case I am assuming two junctions, this is junction 1 and junction 2, and each junction has LEDs. I am using LEDs. In practical circuit we can replace LEDs by high power bulb with relay, and red color is used for stopping, and yellow for waiting, green for moving, that is traffic can move in that particular direction. Here we assume that a passenger going in the north direction, say through this path, he observes his right side LEDs or right side lights. So at a time I am trying to control only two LEDs, and all these red color LEDs are controlled by one port, yellow color LEDs are controlled by another port, and green color LEDs are controlled by another port. And here this is for this is zebra crossroad used for pedestrians. So this is shown here. This is the interface, and initially all LEDs are glowing. It is because I am making use of 8255, and when 8255 is activated, it makes all its output pins high, hence all LEDs are glowing. You see, this is connected to 8255 output through flat ribbon cable. This is 8255. This is another type of microprocessor trainer, 8085 microprocessor trainer only. The difference between the previous trainer and this trainer is, here we are having LCD display instead of 7 segment LED display, and next I am making use of ASCII keyboard instead of hexa keyboard that I have used in the previous case. So here I have written already the program into this. To load that program, first substitute memory address. I have loaded it from 7D10. So this is the program. Okay, and the advantage with this LCD display is we can also, this supports the assemblers. So by using line assembler we can write program in mnemonics. Okay, let me execute the program using burst mode. The address is from 7D10. So now program is under execution. Here processor takes 1 byte and sends to corresponding port. Here you can observe at a time two LEDs are modifying. In this, now two green LEDs are glowing. It indicates that traffic is allowed in that direction. After green, yellow light will glow, and then red light will glow. Now green, next yellow light is glowing, it is for alert, and then red light stops the traffic flow. simultaneously two junctions are controlled as well as these pedestrians. Now green light for pedestrians has glowed, it means pedestrians can walk through. When red light glows, they should not walk, they should not cross the road. So this is how easily we can control traffic signal control signals with the help of processor. The program listing is this, you can download this. The logic is we take the byte to be sent into the to the LEDs into accumulator, and we simply output that to that port, that is all, and we wait for delays. These are the delay subroutines used. Okay. So this is the one application. Next, there are so many other applications you can check in your laboratory. So far, let us see now the summary. So far we have discussed conditions of data transfer, DMA and its advantages, serial I/O data transfer, communication interfaces importance. Here we have seen 8251 and typical applications of microprocessor. We have seen a list, and we have seen one practical application, traffic signal control. So far whatever we have discussed is applicable for 8085 microprocessor, and after this many processors have come, 8086, 8088, 80286, 386, 486 and later Pentium. They have good speed, and they can process more number of bits at a time. But this 8085 processor basics, whatever you have learned, creates a good platform for understanding higher processors too. So this completes this microprocessor topic, and also this particular subject, digital electronics and microprocessors. I wish you good luck. Thank you.